Okay, so welcome everyone back on our lecture room. We have two invited keynote speech now. The first one is given by Renata Wentzcovitch. It's my pleasure to introduce her. Renata is a professor of material science and engineering and applied physics and applied math department of Columbia University. And her research is devoted to computational quantum mechanical studies of materials at extreme conditions, especially planetary materials. And she's also been elected president of the Mineral and Rock Physics section of the American Geophysical Union. And so today's title is Spin Transition in Iron and Lowell Mantle Mineral. And with this, I leave the stage to Renata. Renata, please.
Well, thank you very much for the invitation. It's a pleasure to give this presentation. Matteo was one of my collaborators during these projects. The research that I'm going to discuss today covers essentially 17 years of research. It's during this period, we'd had a long time to make predictions, have them tested, and try to figure out exactly what's going on. And that's the physics that we uncovered in 3D oxides that I want to talk about today. So what you're seeing here is what really has motivated my research for a very long time. So it's trying to understand what's happening in the Earth's interior. The Earth is a dynamic system, very complex system. The difference in temperature between the interior and the surface drives heat flow that in most of the mantle, this thing you are seeing here, is carried by convection. So there is, the mantle is boiling in a geological time scale. Of course, hot material rises, cold material sinks, hot material rising. There is decompression melting near the surface, and that magma spills through these plate boundaries, condenses and forms plates with a certain composition. That's one kind of rock that we see and we know what it is. There is a solid residue left behind. That's the light gray that's beneath, that has a very different composition, and we often see on the surface as well. It comes as volcanic eruptions, or in volcanic eruptions, or sometimes a piece of this mantle is shoved up to the surface. But the bottom line is that we don't have direct samples of the deep mantle, and to a great extent, it's detective work to figure out what's going on down there. The most direct evidence comes from seismology, and for many years we have been relying in models like this. This is density, the shear velocity, and compressional velocity versus depths in the earth. And you see, it has shells, layers, right? And these are shells. It's an onion-like model. Today I'm going to discuss this region between 660 and 2,900 kilometers depth here. This is the lower mantle, and you can see the velocities, the compressional velocity, the shear velocity, and the density. They are essentially very smooth. As you can see here, there are discontinuities in velocity that are well understood and are caused by structural phase transition in the silicate phases that form this region here, the mantle, which is the rocky shell. This is the core, is mainly a liquid iron in the outer core and solid iron in the inner core. But this is the region, the lower mantle, that I'm going to study, temperatures from 2 to 4,000 Kelvin. Today, this is a model that we are trying to understand for a long time. But today there is much more sophisticated model. There are many sophisticated models of velocity. Today we have three-dimensional maps of shear velocity, compressional velocities in the Earth, and this is called seismic tomography. And as you can see, there are lateral. This is 1,500 kilometers depth, and this is the velocity heterogeneity. It's how velocity varies with the angle, And you see velocities can vary, shear velocities can vary by plus or minus 2%. Slow regions, the red regions are usually hot, and this material that is rising. And cold regions is material that is, blue is cold, it's faster, velocities are faster, the material is stiffer, and these are regions that are sinking. And there is a good reason to know, we know that the chemical composition of the material that is sinking, in average, might be similar to that of the mantle, but it might be different as well. So there is that degree of uncertainty. Yes, there are a lot of uncertainties, but there's a lot of qualitative physics here that can be analyzed. And as you will see, there is a great deal of success in trying to in understanding these velocity maps, despite all the uncertainty in chemical composition, temperatures, and etc. Okay, so this is the region that I'm trying to analyze. It's the lower mantle from 23 GPa to 136, 2 to 4,000 Kelvin temperature. And this is the lower mantle. The materials that form this region are these ones. This is a magnesium silicate perovskite. PBNM distortion. It is the main perovskite, the mother of all perovskites, essentially. You know, almost 60% of the volume of the Earth could be just this material here. It has iron, ferrous iron, it can have ferric iron, and it has aluminum as well. This is the second most abundant phase, perhaps 20% volume percent of this region, and that's ferropericlase, which I'm going to do so much in the talk about this material here, because there's a lot of physics of iron here, and it's very similar in the other materials as well. So I'll focus to a great extent on ferropericlase, magnesium iron, solid solution, oxide in the sodium chloride phase. And this is calcium silicate perovskite, another very interesting perovskite, highly anharmonic. It's not very relevant for what I'm going to say today because it exists in very low amount, but it's a very interesting and is still the most mysterious phase in this region. Post-perovskite, there is a phase transition in perovskite to this structure here at around 125 GPa, and this is the structure that exists in the bottom layer here of the mantle. So all these phases, silicates and oxides, except for calcium silicate peroxide, all the others have iron. Iron in ferropericlase could be up to 20%. Iron in perovskite could be about 10%. That's what we usually, so it's not very high concentration, but it's not low either. And these are the temperatures and pressures that we are concerned. So very interesting stuff. So to understand the Earth, you need to calculate bulk modulus and shear modulus of these phases and polycrystalline aggregates, because these rocks are polycrystalline aggregates of more than one of these three minerals, essentially. And we assume in first approximation that is no preferred orientation. It's an aisotropic material. The rocks are isotropic. So you calculate, we need to figure out what's K and G as a function of PTX for each one of them, make the polycrystalline aggregate and try to compare what's happening in the Earth. So that's the goal of this research, understand the Earth's interior by calculating elastic properties. So in 2003 and 2004, it was discovered that iron in ferropericlase and in iron in bridgemanite, the perovskite structure, they undergo what is called a spin transition. That observation, those experiments are perfect, but the consequences that were speculated from these transitions are still not fully confirmed, but nevertheless, it's a very important effect. I'm going to tell you what they are. So 2 papers, 2 years in a row, showing that iron undergoes a spin transition. So what that is. So I'm going to, I think I'm not going to preach to the Pope here. I'm going to go very quickly here. But I have to discuss very carefully the thermodynamic models of this spin transition, because the physics is right here. And then the spin transition in iron in bridgemanite is not what it seems to be. And there is also the ferric iron case and iron with aluminum, which is the case there in the Rio Bridgmanite, and how these things manifest in seismic tomographic models. So you need to understand the elastic properties. So these effects, what is interesting about this research is these effects are not well known when similar phenomena is studied in 3D oxides at ambient conditions or at high temperatures and ambient pressure. It's really experiments at high pressures and temperatures that have been revealing what is the physics of this effect, of these spin transitions. It's very interesting. It's thermodynamics, and thermodynamics has to be carried out varying pressure and temperature at the same time if you want to understand the phenomenon. And fortunately, that's what geochemists, mineral physicists do. And so the methods we start working with Stefano and Matteo in 2004. And so that's the first method we use. And then we moved into the self-consistent U calculation. Qualitatively, the physics does not change, but there are changes in quantitative changes. Density function, of course, we use DFT plus U, DFPT plus U to calculate phonon frequencies now. That's not what we did earlier. And we use quasi-harmonic approximation to understand vibrational free energy, and Vin2K to calculate Moosbauer quadrupole splittings. So here's the spin transition. We have an iron 2 plus in a 3d6 ion in octahedral field, rock salt structure. So we have the T2G EG splitting, and we have 6 electrons. So the first thing, at low pressures, we have 6 electrons spin up, 1 spin down, and this is the this is the crystal field splitting, and 1 electron spin down. This is the Wund's rule energy splitting, right? So as you increase pressure, the crystal field splitting increases, but not so much the Wund's rule energy splitting, and because this the crystal field splitting increases, electrons start transferring to the spin down orbitals, and at a very high pressure. So we start with net 4 electrons with spin up, S equal 2, S equal 1 in this intermediate spin state case, and at very high pressure, the crystal field splitting is so large that only the triplet, T2G triplet, is occupied. So this is what is the spin state change under pressure. And this intermediate spin state is actually a metastable state, very high energy. Actually, there are 2 kinds of intermediate spin states. So the transition is between S equal 2 and S equal 0. So, and what happens when an iron at pressure, under pressure, undergoes this phase change? Well, if you replace a magnesium in Pericles with iron 2, S equal 2 high spin state, the majority electron density is spherical, and you have a minority electron with spin down, with 1 electron spin down, that creates a Jahn-Teller distortion like this. The octahedral FeO octahedral expands this way. When you replace magnesium by a low spin iron, and only the T2G orbitals are occupied, that is the high spin or low spin charge density, and the octahedron contracts. It's smaller than magnesium. Iron 3 plus is smaller than magnesium, and the octahedron contracts. When you go from high spin iron to low spin iron, there is a brutal change in volume of 8%. As far, phase transitions, structural phase transition are usually a couple percent in volume change, 4%. It's not large already, but this octahedra here, it's very, very large volume change. It happens that is a local change. This is a solid solution with at most 20% iron. So that's the calculation we did with non-self-consistent U in 2005. Right. So this is, we calculated a supercell, of course, 64 atoms. We did calculation of several iron concentrations, and fixed the spin, or high spin or low spin, and calculating the enthalpy of both states, both solid solutions. And you see a crossing of the enthalpy around 32 GPa here. And there was, within the accuracy of the calculation, we could not distinguish a change in transition pressure with variable composition. We know today that above 20, around 25 GPa and above, the transition pressure depends on iron, and that's understood and reproduced as well. But at low iron concentration, there is no change in transition pressure, which to me indicated this is a local phenomenon, that spin state change is a local phenomenon. Iron, as if iron were not interacting, we're not seeing each other. It's concentration independent. If you look at the compression curve, the high spin state is blue, and this is 18.75% iron. And the red curve is the low spin. So low spin instead it's denser. The FeO bond length is smaller. And when you superpose to the experimental data, you see that there is a large spin, a crossover here. The transition pressure starts actually at 40-45 GPa and doesn't end until 65 GPa. It's a broad transition pressure range. And you can see the way I interpreted this compression, the experimental compression curve, is that since ions are not interacting with each other, right? Because I don't see a change in transition pressure. So it means that the population of high spin and low spin iron are changing. In other words, high spin and low spin don't live, are existing different ions. And it's not that you have, you know, two configurations interacting on the same iron. And these are the slides that I'm showing that led me to this conclusion. Okay, so here you can see compression curve for the same supercell with 1/3 of irons in the low spin state or 2/3 of iron in the low spin state. So that's essentially the physics. The high spin and low spin, there is a mixed spin region where these configurations are coexisting. So then, if you want, okay, so just for those who want to see what the U's are, and okay, this is the original U calculations we did with non-self-consistent U. This is the low spin U, this is a high spin U, and this is the ones we got. These are self-consistent, and here you also, so it's the high spin U that is quite different here. No, it's the low. It's the high spin U that's quite different. It decreases by more than 3 electron volts, about 3 electron volts. This is the metallic in the LDA, PBE, DFT gives a metallic state. So this U here was calculated from a metallic state. But once you use, if you can, the self-consistent U is smaller essentially. What changes is the transition pressure changes, increases, because you stabilize further. It changes from 32 to almost to 70 GPa essentially, but the behavior is it's quite the same. So here you have intermediate spin states too, with their own use. So here, okay, so this is the transition enthalpy change with the self-consistent U is about 71 GPa here. And this is where the intermediate spin states are. So they are metastable states and they are not populated essentially. So the thermodynamics, so this is physics. So given the fact that I have high spin iron and low spin iron separate in different irons, so I say, okay, I can do the thermodynamics of this system, assuming that I have two end members, high spin ferropericlase and low spin ferropericlase. The end members are solid solutions, and they are not ideal because I'm doing the calculation of magnesium, O, MgO, and FeO together. It's a solid solution, so there is interaction between these end members, right? But in the low, so this is a solid solution built from end members that are solid solutions. N is the low spin fraction, okay? For example, since iron is not very close to iron, and I'm seeing here that doesn't seem to be very much interaction between ions. This is the first model, thermodynamic model we developed. Let's assume that this solid solution between high spin and low spin is ideal. If that is the case, then the volume is a weighted average of the volumes of the N members, right? N is the volume fraction of low spin ferropericlase. If the solution is ideal, the free energy is also a weighted average of the N members, and then we have the mixing entropy here of the two N members. I have formulas for all these terms that if you want to see, I show at the end, but I'm going to skip here, okay? The free energy of the N members, how do I calculate that? Well, it's the Helmholtz free energy plus PV, okay? And the Helmholtz free energy consists of static plus vibrational. And then there is another component here. We call the magnetic entropy or the electronic entropy, which differs from high spin and low spin states. It's this term here in our approach, in our approximations, is this, minus T times the electronic entropy. And this electronic entropy here is, or magnetic entropy, comes from the fact that S equal 2, the high spin state has two, the iron has two S plus 1 possible orientations, and the minority electron can enter in one of three orbitals, T2G orbitals, X, Y, Y, Z, or ZX, right? So I can show you this term here at the end as well if you want to see, but that's where the magnetic or electronic entropy comes from. And this G mix is the G ideal, typical n log of n plus or minus n log of 1 minus n. So then we have this free energy here, right? We minimize this free energy with respect to n, and you get an equilibrium low spin fraction as a function of pressure and temperature. And that's the formula. It's a very neat formula, okay? Delta G is the change in the difference in Gibbs free energy, static plus vibrational, between the high spin and low spin state. So the good thing is that we do calculations in the N members separate, and then you mix them in this way. And M is 3, is the degeneracy of the minority electron in the high spin state, and S plus 1 is the number of magnetic orientation, the spin orientations, right? So this is the degeneracy of the iron in the high spin state. At that point, we couldn't do phonos, and we came up with a vibrational virtual crystal for phonos as well. And I think you understand. And many of the calculations I'm going to show you, we still use this vibrational density of states for the solid solution. Vibrational virtual crystal, you have an idea what it is. The cation is the weighted average of the cations. And in this case is the average elastic, the force constants of the virtual crystal gives the same acoustic phonon dispersion that you get if you calculate the elastic constant of the high spin or low spin states. So it had reproduced the elastic constants, the velocities of the solid solution, as well as, so it's approximate. So this is what we did then. And of course, this doesn't prove that phonons are harmonic, and I can use this vibrational density of states to do thermodynamics, right? But that's what we did then. And recently we have confirmed with the DFT plus U that these phonons are stable. There's a lot more than what I'm going to say here, but this is the essence of what we showed, that phonons in this structure are stable across the spin state change. For example, what I'm showing here are phonon dispersions of ferropericlase, and in the low spin is blue, high spin is red, at 0, 60, 80, and 135 GPa. These are phonon dispersions of a supercell that have been unfolded into the Brillouin zone of the primitive cell. So at 0 GPa, the high spin state is the stable state, but it's the predominant state. But the low spin state unfolded. This is it is stable. There is no unstable mode here. That's what I'm saying. At 135 GPa, when the low spin state predominates, the high spin state is still stable. And this is intermediate situations, 60 and 80 GPa, where you can have both high spin and low spin coexisting in the same pressure range. It's the mixed spin state. We did a lot more than that. We did this is just 3 GPa, 3 mol% of iron, which means it's an isolated iron. We also have results with iron, higher concentrations, irons far from each other, second neighbors, to understand what can produce phonon instabilities and whether my thermodynamics is correct or not. DFT plus U gives a very clean physics, which is these high spin and low spin states have very large volume. It's like a first order phase transition. Both states are stable throughout the entire pressure range. One is metastable when the other is stable and vice versa, but they are not dynamically unstable. Phonons are stable. So this is one of the criticisms that we faced early, but it looks like DFT plus U gives this physics, okay? So here is N of PT versus X that we obtained. This was 2009 already. It was the second paper. So what the phase diagram looks is this. This was is still the non-self-consistent U result. It's with increasing temperature, the mixed spin region, which is the rainbow, widens. Okay, I can discuss why all this happens. This was the middle of the rainbow, the 50-50%, when I did not include vibrations. Inclusion of vibrations, changes this slope here, and is understandable as well why that happens. So it's all cool here. So this is one of the experiments that came out right after our paper of 2006. Okay, this is the 50% range. This is 50%, is the middle of the transition as was measured experimentally in 2007. And this is, I'm sorry, here is not 17% in the experiment, it's 25. And that is very important, okay? In 2010, another experiment came up, and I'm gonna go back to this because this is important too. So this is the 2007 experiment, the STARS. And this is another experiment that came up in 2010 that's much more similar than our results, and that's for 10% iron. Up to 18% or 20% iron, things don't change very much. The phase diagram doesn't change very much. It's above 20% that things start changing. I didn't understand this at that time. I understand very clearly now. So this shift here, white to black, is just a change in this is ad hoc, okay? Because if I want to model the mantle, I wish I could be doing better. My raw ab initio results could be better. But if I want to understand the mantle, I will try to be in better agreement with the experiments. So if I shift the difference in free energy between high spin and low spin at P equals 0 by 0.4 electron volts per iron, I shifted the phase boundary, this middle of the phase boundary, from white to black here. Okay, so this was done ad hoc just for the sake of continue comparing with experiments and making predictions for the mantle. So what happens here is that there are very large anomalies that associated with this crossover, the rainbow, right? So when you at low pressures, everything is normal, thermal expansion is normal. But when you reach 50 GPa and you increase the temperature, what you see is that this anomalous increase in volume, very large anomaly in the thermal expansion, of course, because you are entering the mixed spin region. We're going from low spin to mixed spin, and the volume is increasing anomalously. And this happens, it moves to higher pressures, and the intensity broadens and the intensity of this anomaly decreases. That's something that, yeah. Also, anomalies exist in all thermodynamic quantities. This is a very important one. Book modulus at 50 GPa, if you increase temperature, the book modulus will decrease with increasing temperature, and then will increase again. This is a very important anomaly. Remember that we are trying to figure out what's the consequence of this phenomenon for seismic velocities and what we see in the mantle, right? Okay, so this is the experimental measurement in 25% iron that came out in 2005. It's the difference is that here, the slope is not constant, but it starts with a vertical slope and then broadens, and then the slope becomes vertical again at above above 1500 Kelvin, let's say. I think I understand what's going on here. It has a lot to do with the concentration, 25% iron, and I'm going to show you some new calculations I have done that address this. For example, we had several approximations in our thermodynamic model, but this is a big one. This was so this is the experiment from Japan on 10% iron. This was our rainbow shifted by delta E by 0.4 electron volts per iron. So this is the best agreement we can get, right? So the rainbow here is narrow because of the thermodynamic model. The new thermodynamic model we go beyond the ideal mixing. And that's a brutal calculation because you have to calculate the excess free energy as a function of X. Yes, that's what we did. Supercell calculations with iron in high spin, low spin state, all possible high spin, low spin configurations of that supercell with 18.75% iron at every volume. And I can show you how we calculate the excess free energy as well, but not here. But so it looks like high spin and low spin iron, they are interacting even at low concentrations, but it's a kind of elastic interaction. Irons are not second neighbors here. But there is elastic, there are Young-Teller distortions that can be felt up to the third neighbor, third coordination shell. And this seems to explain the width of the rainbow. Here is a different kind of change. So this is the previous rainbow. Here, the rainbow is more vertical. Why? It's the magnetic entropy. We had the electronic or magnetic entropy was calculated in the atomic limit, right? 2s+1. And so this is the maximum possible entropy. The electronic or magnetic entropy could be lower than that. So here there is no magnetic entropy at all. It's as if the ions that is the minimum value for the magnetic entropy, 0. And that makes it vertical, the rainbow more vertical. So if you have higher iron concentration, it's possible they are interacting. It's possible that the interaction kind of freezes. Actually, I don't know how to justify. It's just an exploration of the effect of different approximations. This is if we remove entirely the magnetic entropy, that's the kind of rainbow we have. And then we add again the excess free energy, and that's what it looks like. So high iron concentration, you have things are different because of the non-ideality of the solid solution, at least. I still don't understand what is happening in the magnetic entropy because my magnetic entropy is very much approximated. What is happening? So the experimental phase diagrams is still a little different, and I think I also understand why the high pressure boundary becomes vertical as well. I can go back and discuss that later, okay? So the state of affairs about elastic anomalies we know exist because it is there in the book modulus. That was the state of affair. Rock salt material, cubic, 3 elastic coefficients, 1, 1, 1, 2, 4, 4, right? The first measurement by impulse stimulated scattering showed that there's softening in all 3 elastic coefficients. Brilliant scattering said yes in C11 and C12, but not in C44. And then in elastic X-ray scattering said there is softening in C44 and C12, but not C11, which was pretty, this is very difficult to measure. And this is all room temperature at high pressures. Measurement of elastic coefficients at high pressures is tough. So here we decided to take a look on this. So for an ideal solid solution, this is the volume, right? It's the weighted average of the end members. The compressibility is the VDP. So the VDP is N, it's also the weighted average of these ratios, volume by book modulus. But there is also an extra term here that comes from the fact that N also varies with P, the low spin fraction. There is a similar formula. This is the inverse book modulus, right? There is a similar formula for the inverse elastic coefficients, the components of the compliance tensor. You can derive this formula here. So the compliance, the components of the compliance tensor of the solid solution is the weighted average of those of the end members plus an anomaly term that depends on the NDP as well. This anomaly here exists for C11 and C12, but not C44. That's what we showed. This alpha term here is 0 for C44, essentially because N doesn't change if the volume doesn't change. Strain, shear strain, epsilon4, does not change the volume of the material. It's epsilon1 and epsilon2 compressive strains that change the volume. Shear strain does not change the volume, therefore does not have the anomaly that is caused by the change in low spin fraction caused by the change in volume. Okay, so shear elastic coefficients don't have anomalies. It's only diagonal and off-diagonal elements of the stress of the elastic constant tensor that have anomalies. And we have been, and the interesting thing, you only need to calculate these elastic coefficients, Sij or compliance coefficients, for the end members, not for the real solid solution. So how do you calculate elastic coefficients for end members? That's how we have always done it. The components of the isothermal elastic constant tensor is the second derivative of the Gibbs free energy with respect to strains. And then the adiabatic elastic coefficients is, you have a correction here. And it depends on the variation of the vibrational entropy with strain. And this is something that we start doing in 1999. We do something, this is brute force. Today we do a semi-analytical calculation. These derivatives here are calculated semi-analytically now as a more efficient method, but that is what is done. That's ultimately what is being done, okay? So at ambient conditions, these are the elastic coefficients of ferropericlase with as a function of concentration, experiments and calculations, okay? As you can see, 300 Kelvin, 0 GPa, we are doing very, very well. This is LDA plus U. LDA gives the best structural properties for oxides and silicates, like these ones that I'm studying. Not metals, but these oxides, yes. And LDA plus U also gives the best structural properties and elastic coefficients. So here, it's what happens. So we calculated the last, so we calculate, this is high spin, we can recalculate for low spin at higher pressure for the entire pressure range, and we mix them according to this formalism here, right? And this is what you get. This is the Book model, adiabatic Book models as a function of pressure at ambient conditions for 10 and 6% iron. Okay, and this is the shear modulus. And these are the three experiments that were so different, but it's the Brillouin scattering that said C44 is 0. That is the one that makes more sense. So there is agreement between experiments and calculation with Brillouin scattering and experiments more than anything else. And this is the compressional velocity, the shear velocity for several experiments with different compositions. And this is ours at 10%. The solid lines is our results at 10% iron. So we are, all we needed to do is that shifting energy between high spin and low spin states to get this 0.4 electron volts per ion. That's because we are not using the self-consistent U at that time, okay? And that is all that it took to have this level of agreement. So it's pretty good, and nobody can measure this at high temperatures. Therefore, we have to rely on our calculations to make predictions at high temperatures. And you saw the rainbows, how the rainbows can vary if you introduce no ideality or get rid of magnetic entropy. So short, very long story short, this is iron in bridgebanite, the main phase of the lower mantle. I'm going to tell you what is happening in ferrous iron in this site very briefly, but this case here is very similar. Iron in the octahedral site is like in ferropericlase, and iron in this site, magnesium site, is just like what I'm going to tell you right now. So this is nice physics. That's why I'm going to emphasize this. So in 2008, there was a paper proposing that there was a new kind of iron 2+, the intermediate spin state, that was stable in that perovskite site. At 0 GPa, there was a Mossbauer quadrupole splitting of 2.4 millimeters per second. At above 30 GPa, they start seeing a second kind of iron with 3.5 quadrupole splitting, 3.5 millimeters per second. And because the quadrupole splitting increased, it could not be a low spin state. The low spin state has 0, it's almost 0 quadrupole splitting. So it could only be the intermediate spin state, right? And at about 60 GPa, the two sets of peaks merged. You had only one kind of quadrupole splitting, and that was the high quadrupole splitting, okay, the high pressure quadrupole splitting at 60 GPa. So what is actually going on? Is there an intermediate spin state here? The answer is no. And we did what you actually find. So let's look for this intermediate spin, low spin, high spin states, right? When you look for high spin states, what means to look for? Well, you will start with iron in a certain position, and then you displace it and optimize structure. This is brute force, no sophisticated method for structural search here. You just displace the iron in all directions and see what you get, right? You start with the low spin, the high spin, low pressure state, which is actually this one here. And you find, you calculate the electronics, the orbital occupancies, and you find this state here with this position in the certain position with the quadrupole splitting 2.3, very similar to the one at 0 pressure. And then you start displacing and you find another iron or you start displacing even more, you find other configurations. So you find several kinds of iron structures with iron in the high spin state and several kinds of structures with iron in the low spin state. No intermediate spin state here, only low spin state. So yes, the quadrupole, you find iron in the high spin state with high quadrupole splitting, but not with low spin state or intermediate spin state with high quadrupole splitting. So what is happening here, and that this is what is happening, what the experimentalists are seeing is not a spin state change. You will start with iron in the magnesium site with this type of electron, minority electron. The other site that you find with high quadrupole splitting has a minority electron in a different orbital. This is T, this is XY, this is going to be YZ or XZ, okay? That's what is happening. And this is the energy that you get by just displacing this ion in the perovskite structure with and without relaxation of neighboring ions. These are the two. So, as I'm saying, like in the high spin, low spin case, you have quadratic curves, energy surfaces here, and the ions are separate. So they coexist. They can coexist in a situation like this. They are both, so that's what the experimentalists are seeing in Moosbauer. Two kinds of high spin iron on different sites with minority electrons on different orbitals. And as you change pressure, the high pressure, high quadrupole splitting state becomes more stable than the low pressure state. And eventually the low pressure state goes away. But this is what is happening. This is not a spin state change. It's a change in orbital occupancy with pressure. So that's it. So what happens in this case here, ferric iron also has a spin state change from high spin to low spin, like ferrous iron in ferropericlase. It's exactly the same situation. And ferric iron here in this site doesn't have a spin state change either. The low spin state here, so this is all the way high spin, 5 electrons with spin up all the way, no changing electronic configuration. So for purpose of understanding elasticity of rocks per ferropericlase, unless you have ferric iron in the B site, this is not going to be important. And this is what aluminum does. Aluminum entering the silicon site removes ferric iron from that site. And ferric iron is only in the A site of perovskite, and there is no spin transition in bridgemanite, which is the most important phase. So there are no elastic anomalies that are important for us are the ones that come from ferropericlase. Bridgemanite is not, although it's the most important phase of the lower mantle, it doesn't contribute serious elastic anomalies.
Renata, sorry for the interruption. Just 5 minutes.
Okay. All right. Very good. So let me tell you what is the consequence for the mantle, and then we are going to discuss, right? So this is the consequence for the mantle. It's right here. So this is the rainbow. As a function of temperature, so we have, this is ferropericlase, only one mineral. As a function of temperature, this is, we are sitting at 75 GPa, which means 1,500 kilometers depth. The book modulus in ferropericlase varies like that because 75 GPa is right here. I start in the low spin state, and then I increase temperature, and I go through the mixed spin region here. And that's when you have this large anomaly in the book modulus. The more iron you have, the larger the anomaly. So here I have two concentrations, 12 and 21, okay? And no serious anomaly in the shear modulus or on the density. So if you have this happening there, suppose that, as I showed, that plume, right? Going through the lower, rising from the core mantle boundary through the lower mantle. So you have a certain temperature at a certain point, and then you move laterally a couple of kilometers and the temperature is higher. So what happens with the book modulus? If you increase the temperature, the book modulus will increase and the shear modulus will decrease. So essentially you increase the temperature, the shear velocity decreases. That's how we see low velocities in the tomographic maps, in the seismic tomography maps. The book modulus, the shear modulus will decrease with temperature and the book modulus will increase with temperature. So this VP here gets an anomaly. It might not go anywhere. If the GDT is equal to KDT, VP doesn't change with temperature, right? Of course, this K here is much more important, but remember, I have a rock, 78% ferropericlase without spin, Bridgmanite without spin transition, some calcium silicate, and then my ferropericlase. So the anomalies in K can also be seen in the rock, in the aggregate, which is the elastic properties of the rock are calculated with Voigt-Royce-Hill averages. So VP, and so it happens that VS. Okay, so let me go. Oops, I pointing the wrong direction. So if you have an anomaly, a hot anomaly through the mantle, this is what you see. The signature of a hot anomaly in the mantle. That's what you should expect. The anomaly should be in S velocity maps. In the P velocity maps, because of this insensitivity, this anomaly in the book modulus, the low velocity anomaly gets disrupted. The book modulus is VP is less sensitive to temperature variations at a constant pressure, right? We call lateral temperature variation. So this is how this signature of the spin transition should show up in the mantle. It happens that this was being seen for quite some time and people didn't understand, and believe me, seismologists blamed this type of anomaly on many quantities, on many things. For example, let me show, these are places where we have hotspots, volcanoes like Hawaii. The source could be in the core mantle boundary. So how do these images look like? These are all hotspots around in the Pacific, around the Earth. But look at this picture of Hawaii. This is a P velocity map. It's not shear velocity map. This is a P. This is Iceland, the same kind. Samoa, Canary, Cape Verde. There are many hotspots, volcanoes that have P velocity maps that look like this. Shear velocity maps were not correlating well with this, so people didn't believe that, you know, this moduli would be affected differently by temperature. So because I have a very short time, I'm going to cut here because I could show you so many interesting correlations. This is a shear velocity map 2018. After we said that they could see these plumes in shear velocity maps, they really start looking for example, this is one paper that was published in 2015. They were able to detect these plumes coming from the core mantle boundary. This Yellowstone, the mother of all volcanoes in the Earth. And anomalies could also happen in cold anomalies, plates, cold regions sinking. But let me cut short here. Oops, I didn't include here. Because, all right. So this is, so these are plates sinking to the mantle in the same depth range. You have the same kind of problem there. These images disappear in compressional velocity maps. I could say a little bit more, but I'm going to cut here and leave you with this image. These maps that I have, these are called Volt maps. These tomographic maps, they differ from each other. So you look at this is sort of average shear velocity map and P velocity maps. These blue are cold regions. This is a cut in the Pacific. This cold region here, this blue region is one plate that has subducting in the mantle. This is the west wave image of that plate. This is the P wave image of that plate. This is another very important plate far along under the Americas. This is the S image. This is the P image. You see the plates disappearing somewhere. And these are hot plumes coming from the core mantle boundary. This is the African super plume. You see here P, S image, and P image. The P image is much fainter. So this is the kind of relationship between velocities, compressional and shear velocity, that this is the type of relationship that you expect in the presence of spin transition in iron. Okay, so what we are aiming at, anharmonic effects. Of course, I showed the phonon calculations, but there's a lot more than harmonic phonons that could be going on here. So anharmonic effects, including anharmonic effects across the spin transition, that's what we are doing right now. Search for new phases with high iron content. That's also something that we are focused on. Multi-phase equilibrium, because every time you have a rock, the chemical potential of all species has to be the same in all phases. If you have a different kind of iron, the chemical potential is going to change, and the composition of these coexisting mineral phases changes as well. And they're going to much higher pressures to understand terrestrial exoplanets. So these are the people who I should really thank for collaboration throughout these years. So thank you very much for your attention. And I'm ready to answer questions.
Thank you very much, Renata. Thank you very much. I see on slide a number of questions. Then, for the sake of time, perhaps I can just select a couple and try to synthesize.
Right. I will stop sharing.
So one question is somehow methodological. It is working at these volumes. That of course we can do within our simulations. So what is the reliability of our quantum espresso simulations at these ranges? Can you comment on that? I think probably this comes back to pseudopotentials.
Yes. Well, up to 135 GPa, iron with 8 electrons is pretty good. You don't need 16 iron with 16 electrons. You need that at above 150 GPa. You need iron with 16 electrons if you want it to be accurate. Yes, as I said, let me show you. Go back here to perhaps. I think even with the non-self-consistent U, that here, for example, right? Look, U changes upon self-consistence. The high spin U decreases by 3 electron volts. But the compression curve, this is experiment, and this is calculation. Blue high spin, red low spin. When you add vibrational effects, this volume increases a little bit, but our concentration is already a little smaller, it's larger than the experiments. Okay, so it's excellent agreement between the volumes at 300 Kelvin and the volumes measured at 300 Kelvin. The volume compression curve doesn't change very much even with the self-consistent U. The energy, the transition pressure changes from 32 to 71. That's quantitative change, but qualitatively, the compression curve doesn't change and the phenomenology does not change. There is a lot more, I know, yeah.
Thanks. Mm-hmm. So another question that is instead more related to the high spin and low spin phases. Could you please elaborate on the interaction between iron, high spin and low spin? For example, for a supercell that includes both high spin and low spin iron, does the high spin iron has any preference for its neighbors? This is
which kind of neighbor?
Yeah.
Which kind of neighbor? Yes, It does. Actually, U also changes when you change the, if you have two high spin irons, one with parallel or anti-parallel spins, U changes likely, okay? The preferences for anti-parallel neighbors, when they are neighbors. That's when you have irons or second neighbors, that it is, of course, no ideal solid solution. And that's what, it's what we do. We have done one non-ideal solid solution calculation. Here, you can see how the volume changes, okay? So this is iron, this is 300 Kelvin calculation. Iron in the high spin state, undergoing the spin state change, right? So this is the ideal solid solution model. Here, it's high spin, it's N members are N equal 1 is low spin, N equals 0 is the high spin. Ideal solid solution, you interpolate the energy as a function linearly with N, okay? The static energy. And then you do a calculations of all, this is the excess free energy that you get, and this is the Boltzmann average, actually, with temperature, of the energy of all possible configurations, parallel and anti-parallel. This is truly no ideal solid solution, okay? And this is the Boltzmann average of all these configurations that you get. It doesn't vary much with temperature. It's really, it's a function of N. This is the interaction between high spin and low spin iron. And then you include this excess free energy here in the non-ideal solid solution model. Again, this is a numerical function. And then instead of getting a nice clean formula for the N that minimizes the free energy, you get a numerical, an equation that has a numerical term. But look how the compression curve changes when you include the interaction between irons. You have the red dashed line is ideal solid solution, okay? With magnetic entropy and no magnetic entropy, because that's our uncertainty. I don't know exactly how to do that calculation yet. And then is the non-ideal, is the blue, with magnetic entropy, without magnetic entropy. You see, it's in much better agreement with the experiment than the ideal solid solution. The non-ideal, the interaction between iron, and honestly, I don't have a model. I just have numerical brute force calculations for this particular case. That's all. It does matter in the compression curve. But look at the agreement on the magnitude of the volume. It's very good agreement, with or without. Of course, with no ideal solid solution is much better, okay? But the pure high spin and the pure low spin state, the agreement is quite good.
Thanks. Thanks a lot, Renata. Thanks a lot. Unfortunately, so there are some more questions on Slack. Yep. Unfortunately, we need to go ahead with the schedule of the afternoon. If you are connected on Slack, you're free and welcome to go through the questions and answer yourself. Okay. So we'll give it a pass later on. So okay. We thank a lot. Thanks again, Renata, for a very nice and inspirational talk.